engineering at Hebrew University of Jerusalem, giant in the field of algorithms, also combinatorics, applications of geometry and analysis to those areas, an ISI highly cited researcher. I'm very happy to have Nati telling us about graphs as geometric objects. Welcome, Nati.
Thank you. Okay, so I think by now, with all the previous talks that we heard, perhaps the first few slides are completely redundant. We already heard about how to investigate important algorithmic questions such as flows on networks. We also heard how the brains of animals are when they navigate, is modeled after a torus, etc. But I hope to convince you that there is still huge territories in the interaction between graphs and geometry that we still understand too little about. So just to be on the same page, these are my basic premises, that everything fundamental that you know in geometry has an interesting combinatorial counterpart. And again, just to have the language correct, geodesic geometry or geodetic geometry is, for example, what you do in Riemannian surfaces when you determine how to go from one point to the other. There is a geodetic path that connects them. Okay, so that we already said, and let me, actually, it was quite a surprise for me to discover this old mention. I don't know how many people are familiar with the name of Øystein Ore, but he wrote he was a Danish mathematician, both in graph theory and group theory, very influential. And in one of the first books, modern books in graph theory, he introduced the notion of a geodetic graph. He calls a graph geodetic if between any two vertices in the graph, there is a unique shortest path. So some examples, trees, complete graphs, odd cycles, and perhaps one more interesting one is Petersen's graph, which you see here. And why does Petersen graph have this property? This graph will reappear later on in a different context or somewhat related context. This is a graph with the diameter 2 and girth 5, which means every two vertices are either connected by an edge or by a unique path of length 2. So in particular, that's a geodetic graph. And he raised the question of, can we characterize these graphs? And it is still very far from being solved. So to simplify matters or to concentrate or thought about this, I only want to restrict myself to graphs in which, first of all, two connected. That's quite obvious that any cut point really trivializes the question. And so I want to assume two connected. And I also want to assume that all the vertices have degree at least 3, and that makes the problem more combinatorial and more geometric. And so I want to formulate a conjecture that such a graph, so geodetic, two connected, all vertex degree are at least 3. There is an absolute upper bound on the diameter of such graphs. The best construction that we know at the moment for this has diameter 5. Perhaps that's the most. So you see, such very simple notions are already very, very old questions, and we know very little about them. So there is, of course, we actually saw them even today. There is, of course, a very strong connection between graphs and metric spaces. If you give me any connected graph and you put positive weights on the edges, then that determines a distance between any two vertices, the sum of the length of the edges in a shortest path. And just to simplify matters, I'm completely going to ignore tie breaking because, for example, if I choose the edge length at random, that will happen with probability 0. So no mention of tie breaking at all. But even this, which is really so simple, very soon will lead us to very simple questions that we still don't know the answer for. So a path system, a weight system on the edges induces a path system on the graph. It's a consistent path system. So between any two vertices, I have a chosen path, and consistency means that if the path, the chosen path from U to V goes via X and Y, then the subpath between X and Y is the chosen path between X and Y. So this is a consistent path system. This is the main thing about which we're going to be talking today. Okay, so already here are some questions that we still don't know the answer for. So suppose I give you two different weight systems on the edges. I want to consider them equivalent if they determine the same path system. And even the following very simple questions we don't know the answer to. I give you a graph. How many distinct equivalence classes are there? How small can this number be? This, I think we know the answer to, but I won't go into that. How large can it be? There we have a conjecture, but still it's not known. So even these very simple things which you can explain to students in the more or less second class in a class of algorithm or graph theory remain open. So this is the first question that my student Daniel Sisma, with whom we did this work, asked ourselves: does every consistent path system come from a collection of edge length? And I call a graph for which the answer is yes, metrizable, and otherwise non-metrizable. So we're asking, are all two connected graphs metrizable? Turns out the answer is no. And let's start with an example. So you already remember the Petersen graph, and you remember I told you that every two vertices are either adjacent or are connected by a unique path of length 2. So my path system, my consistent path system, is mostly going to use the obvious thing. If they're adjacent, then I use the edge. If they're distance 2, mostly I connect them by the path of length 2. And there are 5 exceptions, 5 exceptional pairs. You see, for example, the red path that goes from 2 to 1 to 6 to 8, and all other, the green one, and so on and so forth. These, although they can be connected by 2-hop, I chose this 3-hop connection between them. It's very easy to verify that this is a consistent path system. And now I want to show you that this path system consistent path system doesn't come from any system of length on the edges. Why? So suppose suppose I associate a positive number wij to every edge ij in the graph. And then I can write some inequalities, right? The first inequality that you see here says that in order to go from 2 to 8, the 3-hop path that I chose is no longer than the obvious 2-hop path. And you write all these inequalities, you sum them up, and you conclude that all the edges in the middle of this picture have non-positive weights, which is, of course, a contradiction. So we prove that the Petersen graph is non-metrical, non-metrizable, and we actually found a consistent path system that is non-metric. So what do we know? So I don't have time to really tell you today too many technical things. Perhaps I'll show you one small proof just for taste. But these are the main discoveries that Daniel and I have made. So metrizability is rare. I'll make this more concrete later. So, but in any sense of the word, almost all graphs are non-metrizable. Yet there are infinitely many non-trivial, two-connected metrizable graphs. Every outer planar graph is metrizable. And if you don't remember the definition, I'll tell you later on. And something that really surprised me quite a bit, I give you a graph and I ask you, is it metrizable or not? This can be answered in polynomial time. But I must say that one lesson that this investigation taught me is, which supposedly we know this very well, but it's quite striking when you see this so clearly. There is a big difference between solvable and polynomial time, and something that we really understand. So equivalent, we spoke about consistent path system. There is something equivalent to it, which is a consistent tree system. So this is a collection of spanning tree. You can think of, there is one rooted at every vertex. And consistency means that in the tree, the UV path in the tree rooted at U and the tree rooted at V are identical. And the two notions are equivalent. That's very easy to show. For a path system, you move to a tree by simply collecting all the paths that go to the root, and this creates a tree. And it's also very easy to go from tree systems to path systems. So the two notions are equivalent. So let me give you, so you can, the subject is really very, very rich. I mean, I only give you a first taste of it, and there are lots of very basic things that we would like to know and we still do not know. But just for a sense, you can speak also about partial path systems that are consistent. But if you look at this diagram that we have here, you can easily convince yourself that although the partial one is consistent, it cannot be extended to a consistent path, full path system that is consistent. But moving from a subgraph to the whole graph, that can be done. So very basic things that we were still mysterious. So just again to remind, to recap. So I give you a graph, I give you a path system. I call the path system consistent path system. I call it metrizable if it can be realized by edge weights, and strictly metrizable if the inequalities are strict. And according to that, I call the graph G metrizable or strictly metrizable. And so one non-metric path, consistent path system already makes the graph non-metrizable. That's just I'm just recapping repeating the basic definitions. And metrizability is determined by the two connected components of the graph. So in fact, it's enough to consider two connected graphs in this discussion. So I want to very briefly, so, there is a mathematical talk without a proof is considered missing. So I'm not going to prove to you, but just quickly sketch to you just a tiny part of a bigger theorem that I mentioned already. So an outer planar graph is a graph which you can draw in the plane in such a way that all the vertices reside on the outer boundary. And the simplest such graphs is a cycle. So all these graphs are metrizable. And let me briefly describe to you how we prove that cycles are metrizable. So let me again repeat. If I give you a path system, a consistent path system on a cycle, then there are edge lengths that will give you that. It comes from some collection of edge lengths. So it belongs to the exception and not the rule. So let's try to understand how this goes. So really, so here we're using this notion of a consistent tree system. So a subtree of the cycle is simply remove an edge. So in order to describe a consistent path system on a tree system on the cycle, every vertex should tell which edge it removes in order to choose or to determine its a tree in the consistent tree system. So you can think about the whole thing as a mapping from vertices to edges. So like here, the blue vertex chooses the blue edge, which means the tree rooted at the blue vertex is the cycle minus the blue edge, etc. And the first step that you prove is that for such a function to correspond to a consistent path system, it has to be crossing. As you see here, the pink and the blue edge cross each other. And every two such things should cross each other, and if and only for such a system to be consistent. And then what you prove is that you can shrink or contract edges in the graph and still in the cycle and still maintain a consistent path system or consistent tree system. And then eventually, if you have something like in the picture on the left, you see there are two yellow vertices that both choose this yellow edge across, then you can shrink the white edge, the edge that contains them. And the theorem says that if you do this, if you have a consistent tree system on the cycle, and you shrink all these white edges like here, then eventually you end up with an odd cycle and the standard metric on the odd cycle, and that's essentially the proof that cycles are metrizable. Okay, so let's talk about this family of metrizable graphs. And as it turns out, metrizable graphs are closed under taking topological minors. So let me go over this statement and make sure that we all understand what that means. So I say that if the graph G contains a subgraph, which is an isomorphic to a subdivision of H, then we say that H is a topological minor of G. So let me repeat the sentence. It's a little bit of a mouthful, so let me say this again. The class of metrizable graphs is closed under taking topological minors. Stated differently, if a graph has a subdivision, contains a subgraph that's a subdivision of a non-metrizable graph, that makes the big graph also non-metrizable. So this gives me a way of proving that certain graphs are non-metrizable. The obvious thing for anyone who knows about the important developments in modern graph theory, the obvious question to ask is it a minor closed family? That's something we know much more about thanks to the fantastic theory of Robertson and Seymour. But the answer is no, this is not a minor closed family. This is an example. The graph on the left is metrizable, but if you shrink the top edge, then you get the graph on the right, which is non-metrizable. So it is not a minor closed family. So let me say something about the proof of our main theorem, or one of our main theorems. I already said, I haven't been specific about this, but I will in 2 minutes, that essentially a vast majority of all graphs are non-metrizable. How did we prove it? I don't think this would win a beauty contest, but it's still quite a lot of work involved in this. So we found these 10 graphs that appear here. We found them using the computer, and we found for each one of them a consistent path system that's non-metrical. How did we prove that it's non-metrical? In the same way that we proved it for the Petersen. We wrote the inequalities and we got a contradiction just using linear programming. And now using the fact that metrizable graphs are closed under taking a topological minor, we use these as building blocks. So I just want to stress this point, which is rather, I think, interesting, especially for computer scientists. I don't know that we would be able to prove these things by hand. Perhaps yes, but I doubt it. So while all these 10 graphs were found by a computer and were, essential building blocks for the proofs, the fact that they are non-metrizable is very easily verifiable by humans. So if you want, bring home the notion of P versus NP, it's very easy to verify, very easy for a human to verify, quite not so easy to find by humans. So essentially we have two main ways to prove non-metrizability, either to construct an explicit path system like that's consistent and non-realizable, like we did with the Petersen graph, or find in G a subdivision of a non-metrizable graph from this collection that we call the zoo. And in fact, I won't elaborate on this, but this allows you to give a different proof for the non-metrizability of the Petersen graph. So now I can be more specific about what I mean, that essentially almost all graphs are non-metrizable. So you can read the theorem, but let me skip it and come to the conclusions, which are, easier to swallow. So every 3 connected graph with at least 8 vertices is non-metrizable. Every 2 connected non-planar graph with at least 8 vertices is non-metrizable. Every 2 connected graph with a minimum degree at least 3, at least 13 vertices is non-metrizable. So if you have any sense of what any notion of random graphs look like, then you realize that it's not so easy. While there exist metrizable graphs, they are quite rare. Okay, so let me explain now that we do know. I told you that cycles are metrizable, but actually this is a special case of a more general theorem which says that every outer planar graph is strictly metrizable. Outer planar means, again, that it can be drawn in the plane in such a way that all the vertices are on the outer boundary. And here you see a few examples. So the quick proof that I sketched for you about the cycles, it can be considered, as a small exercise towards the proof of this. It's quite a complicated proof. Okay, so how come we're able? I also mentioned as a third thing that we discovered, I said that we can decide whether a given graph is metrizable or not. So while it is, so we have a method which we already saw using linear programming. So it's relatively, we have all you still need to know a few tricks of the trade in linear programming to do this, but they're quite standard for people who do this. So using this linear programming approach, that gives you a proof that humans can verify that a given graph is non-metrizable. But although, as I said, we can decide it in polynomial time, the proofs of metrizability are still mysterious to us. So what happens here? Since this class is closed under topological minors, there is always a list of the minimal objects which don't fall in the class. So they are non-metrizable, but if you any proper topological minor of them is metrizable. So we want to understand what this is. So just to illustrate, so you're with me on this. So I think you all know, or most of you know, the classical theorem of Kuratowski, which characterizes planarity. A graph is planar if and only if it doesn't contain either K5 or neither K5 nor K33 as topological minors. And the great theorem of Robertson and Seymour, one of the greatest accomplishments of modern combinatorics, says that every minor closed family is characterized by a finite list of forbidden graphs. So the only surprising word in this theorem is the finiteness. That there is such a list is nothing, but the fact that it's finite, that's the big achievement here. It's a huge theorem. But the analogous theorem is not true for topological minors. So here you have a infinite family of graphs, which shows that the analogous thing for topological minors doesn't hold. And yet there is enough structure, I don't have time to elaborate on this, which allows us to conclude that the list of minimal counterexamples, so to speak, is finite. And this in principle says that we have a polynomial time algorithm to decide metrizability, but this is very, very far from being an actual algorithm that we can run and use. So there is still a lot of mystery to unveil here, which we don't understand. So concretely, I want to ask, can we find the full list of topologically minimal non-metrizable graphs? That would be, we know that it's a finite list, but I have no idea, if it's 100 graphs or 100 to the 100 to the 100, no idea. And the thing that I mentioned before, so can we find proof certificates for metrizability that humans can understand. This is still at the moment open. So let me just say a little word about these approaches with linear programming. You have such systems of inequalities like we saw before. And on the face of it, it's problematic because these systems are exponentially large, but using ellipsoids and these kind of things, these systems can be solved. So non-metrizability can be done efficiently, I mean, in a way that we understand, but metrizability is still a mystery. And with this, I'll stop. Thank you very much.
Thanks, Nati. Questions? Oh, if not, we'll move on to our next speaker. Let's thank Nati again.